Yeah.
Okay,
Yep.
thank you so much. Uh, Before I get started today, I want to make announcement. Today you're going to see your result for midterm two. Okay, so latest in the evening. Okay, and I'm actually going to bring your exam document when I'm coming to this class on Friday. Okay, so once again, I want to welcome you to today's topic that we actually call Van Bertalanffy growth models. Of course, before now, we started what I called nonlinear models. And of course, I introduced it to nonlinear model on Monday. I told you, generally speaking, the nonlinear model can be divided into intrinsically linear and intrinsically nonlinear model. The intrinsically linear model is when the nonlinear model can actually be linearized. When it can be linearized, you can actually use a linear approach to estimate parameters in that model. And on the other hand, the non-intrinsically linear model is actually the one you cannot linearize. Of course, we got a special approach to estimate our parameters in such model. And I remember I justified on Monday the importance of using non-linear model. Okay, I talk about parsimony, where we're going to have a few numbers of parameters to be estimated, and the parsimony will lead to interpretability, because what makes a model to be difficult to interpret is when you got a lot of parameters in the model, maybe because you got a lot of explanatory variables. So instead of you to use a lot of explanatory variables, maybe uh, you can actually use a nonlinear function. And I remember I walk you through some form of nonlinear function on particularly the one for growth model, where we use example from US population. We use a logistic growth model on Monday. I walk you through how you're going to go about that. And I also walk you through an example where we're looking at the relationship between rates and the concentration, where we use the Markowitz model. But today, the focus is going to be on Van Bertalanffy growth model. Of course, in my outline, I've just reviewed nonlinear models now, talking about what we did on Monday. And of course, this lecture notes, we actually focus on Van Bertalanffy growth model. Now, to the Van Bertalanffy growth model, this was actually introduced by Van Bertalanffy, an Austrian biologist, because this particular growth model is very, very applicable in ecology, not only in ecology, in fishery in general, because we actually, they use it to model, predicting the length of fish, given the age of fish. Of course, the length of fish it has economic value. You know that, right? Not only the length, even the weight. Okay, so and this model has been proved to be a very good model to capture that relationship. Okay, so I'm going to show you the mathematical architecture of the model now. That's what I'm showing in equation 1. You know, when you take a look at this, I'm actually going to call this guy a nonlinear mean function. You remember when we're working with a linear, when we are given multiple or simple linear regression model, we always have what we call a mean function, right? Which is going to be the expected value of the response variable given the predictor. Now, when you take a look at the equation 1, that is the expected value of the length of a particular animal at a time t, okay, well, which is equal to L infinity. You know, the L infinity here is the asymptotic average length. You know, what I mean by the asymptotic average length in fishery is the asymptotic length at which the growth is 0. When the growth is 0, what is the asymptotic length? Okay, then we have a K, which is called a Brody growth rate coefficient. Some statisticians or scientists, they believe it's constant, but some believe it is not. Because particularly Vaughan in 1960, when he was trying to look at the age of a shark, he discovered that when shark is getting, you know, shark, okay, there's a big fish called shark. When the shark is getting older, right, that K will be getting smaller. That was what he actually observed. Okay, now the T0 is a modeling artifact, okay, which represent the time or age when the average length was 0. Okay, so I present to you the Van Bertalanffy growth model. But let me tell you this. This particular model was actually derived using the first principle. This is not the original model. The origin of this model, we follow what I call a differential equation in mathematics. Has any one of you heard about differential equation, right? Yeah, there's a differential equation. Take a look at this. You know, it was noticed that the rate of change of the length of a particular animal under investigation at time t is directly proportional to the difference between the L infinity and L of t. You know, when it's directly proportional to that difference, then we're going to introduce a constant of proportionality, which is K. Now, equation 1 is a first order differential equation. That was a statement from biological theory. And looking at the biological theory, we actually formulate the mathematical representation of that theory about the rate at which the length of that particular animal change. Does that make sense? So when you look at equation 1 now, that is the first order differential equation. And you know what? That first order differential equation needs to be solved for L of t. And we're actually going to use, we got some method that we use to solve the first order differential equation. I remember when I was doing calculus, we have the method of separating variable. We have the method of linear equation that we call if, integration factor, and so on like that. We have homogeneous, but this guy here can be separated. When you look at, you know, in separating this now, I want L of t to go to, you know, L of t. And that's exactly what you see in the second line. Do you see the second line? Okay, that was true separation. When you go to the third line, you're basically going to see in the third line, we only have L of t, and L of infinity. We've been able to separate that. Okay, and when we separate, you know, that, what we're actually going to do is, to integrate that. We can integrate both sides. Integrating K, that will be KT plus C, because I'm integrating with respect to T. That very C is going to be a constant of integration. I think I'm going to show this for you to be able to see. Those of you online, I need you to, if you cannot see what I'm going to write, please let me know. Now, initially, we have, DDLT, the T. Those of you online, can you confirm if you can see what I'm writing on the board?
Just put the camera a little bit up.
Okay, a little bit up. Okay, so what I'm gonna do is, because I can, maybe what I'm gonna do is to bring this one down. What about 9? Do you see what I'm writing now?
Yes.
Okay, you can
Yep,
see, you can see now, right?
Yeah.
Okay.
Yeah.
Now, that guy equal K L of infinity, okay, minus L of T. If you take a look at what I have now, okay, so what I want to do, this is a differential equation. Solving a differential equation, I'm actually going to use the method of separating a variable. So I'm actually going to have this guy divided by L infinity minus L of that, which is going to be equal to K dt. Okay, since I've been able to separate that, then I'm actually going to put integral to both sides. Okay, I'm putting integral to both sides. Okay, now putting integral to the side, I'm actually I want to integrate days. I'm integrating 1 here with respect to the L of T. Okay, and if I differentiate this guy, if I have this guy, because when I differentiate with respect to L of T, that will give me -1. When I decide to put a -1 here and I put a negative here, negative is going to cancel out, right? Now there's a particular law in mathematics. When I have a function like this, when I want to integrate, when I differentiate the denominator and I have a numerator, I'm just going to write the log of the denominator. Don't forget there's a minus here. And this guy is going to be equal to KT plus C. That was how you got the minus log L of infinity, L of T equal to KT plus C. Okay? And every other one is going to go. Okay? So take a look at that. Now, when you take a look at what I got now, I got a log. The log is going to go to the other side and become exponential. I'm using a natural log. Then I'm going to be left with L infinity, L of T. When the log goes to the other side, the exponential is going to carry K. It's basically going to carry what you see now, minus KT plus C. But why do we have a minus? Because of the minus here. The minus here is the one that is going to that's going to make it the minus. Y doesn't change C. C is just a constant. Okay? And when exponential carry that, we're going to have what you have right now. An exponential raised to power constant will give another constant, right? That was why I said D. Exponential raised to power constant is going to be D. Then I still have this guy. And finally, if this is what I actually have now, okay, if I now want to get L of T, then this is what I'm going to get for L of T. Okay? Now, when I get that, because this is a function of D, right? I need to solve my D. How am I going to solve how am I to don't forget D is a constant, right? Then I'm actually going to solve D. I'm going to assume what I call initial value problem. Okay, which I'm going to say, okay, when t equal to 0, what's going to be the L of t? Okay, so what I'm going to do now, I'm using this guy, L of t 0 equal to 0. Then I'm going to equate that to 0. You see that? What am I equating to 0? I'm equating L of t to 0. I'm assuming initial, stuff. Then that will enable me to solve for D because I need my D. When I solve for D now, that's what I got. Then after getting this very D now, I will go back into where I have D in the module. Then I'm going to plug that in. When I plug that in, that we automatically, when I simplify all of that, I'm actually going to have this guy here, which is the formula derived. This is a Bertalanffy growth model. Okay, so what if we ask you to derive the Bertalanffy growth model? Of course, you're actually going to start all the way from differential equation. Okay, so I'm going to go to the next question, to the next slide now. Now, it is not only where we want to predict length of fish or length of a particular animal that we can use Bertalanffy. We can also have the weight version. This is going to be the weight version. Okay, this is going to be the weight version. And the weight actually, if you take a look at the first one here, right? Because what is of economic value to us is going to be the length of fish and the weight of fish. I want to believe those in Alaska, they will take what I'm talking about seriously because they want to make more money. They need to know, I know they're going to be interested in the length of the fish, and not only that, the weight of the fish. The more the weight, probably the more the money. And the weight of the fish can be written as the product of A and the L of t. Of course, the weights depend on the length. That's what we're trying to say here, multiplicatively. So what I bring in here is bringing in the L of t that we derived before, so that we'll be able to have the weight at any point in time in terms of this. And of course, this guy here is basically going to be the weight W infinity. Take a look at what I have. Any question on this derivation? Any question, whether in person or online? Any question?
No.
Okay. Now, let's now look at the animal we want to focus on. Oh, this is beautiful. You can see that, right? This is taken from, it's an Atlantic croaker from Maryland, the Maryland DNR website. Okay. Now, you know what I'm going to walk you through now. When we have data set on fish, how can we fit Bertalanffy growth model? I'm going to walk you into this now. Of course, my TA is going to walk you through all this. If you want to have access to the data set now and how to perform operation on Bertalanffy growth model, you need to load the FSA data, NLS true, because the FSA data is just where we're getting our data set from. The NLS2, of course, we're going to make use of non-linear least square. And the name of the data is Croaker2. Croaker2. And if you take a look at this, the next step now, because in the Croaker data, we got both male and female fish. And the first one, we basically want to focus on male. Does that make sense? If you take a look at, we want to focus, that was why we said the subset of that data set, we're focusing on male. Now, if I want to work with a non-linear model, don't forget, the Bertalanffy group model, It's a nonlinear model. We need to first look for a way to get a very good initial value. You get what I mean? So if I want to get a very good initial value now, let's first, get the estimate of a very good initial value that is going to work. Where I'm actually, and that was what I call SV typical, or less than minus VB start. The T1 is a response variable here, and this is age. Okay, with T1 now, maybe we're talking about length. That's a data set on length. And the age, and we're using a data CRM. The CRM only focus on the male fish. We're only interested in the male fish. Now, I'm actually going to have 3 estimates. Don't forget, if you go back to the Bertalanffy growth model, we need information about the parameter, the L infinity, K, and T0, right? So we are actually trying to figure out what this guy is going to give me now. These are the initial values that we're going to start with. Okay, it's trying to tell you the L infinity is going to be 340.5069. K is going to be 0.3517. And T0 is going to be negative 1.6732. Those are not my final answer. They're just the initial values. It's like having an initial guess. And you can only have a best initial guess when you first like do what I'm doing now. Now I'm ready now to use the Bertalanffy growth model, where I'm actually regressing the response that I call T1 here on the model. If you take a look at that, that's how to write the Bertalanffy model in R. When I wrote the model, I want to fit now. What do I want to fit? NLS. That's a non-linear least square. That was the reason why I loaded a package, the NLS tools. Now, when I do the overview, oh my God, I'm actually going to have results. Okay, this is just to show you the data, maybe the first 6 data point, age, and the length. Take a look at that. And of course, there's something I wanted to see here. When you take a look at the age here, I want to take a look at that. The age is repeated. You can see 2, 2, 2, 2, 2, right? Age repeated, right? But the size is kind of different. Okay. Now, when I do the overview of this guy that I fitted here using my initial values that I got, this is going to be the results. Now, the result is going to look like linear regression model, like linear regression output that you normally have, where you're going to have estimate the standard error, t-value, and a p-value. And of course, we take a look at the estimate now. We got our L infinity, K, and T0. Take a look at that. Now we can also get a confidence interval. Okay. What we actually have here, what you have in the first column is a point estimate. I told you the other time, a point estimate could be wrong or right, even though if you have done what is necessary. And now can we tell whether the estimate that we got is reliable? It's more or less like, how do we show what we get in the survey reflects the general view of the population? We need a confidence interval for the parameters. So this is a confidence interval now for the parameters, each of them. Take a look at that. Now, we're also going to have a correlation matrix. Let me tell you this. When you're talking about growth model, then it means you have a time component, right? When you have a time component, then the assumptions of independence does not hold anymore. And that is, if the assumptions of independence does not hold anymore, then it means there's going to be correlation. It means the parameters will be correlated. Now, and that is why, take a look at the correlation matrix. What you see in the correlation matrix, you got a very high values for correlation between any two pairs of parameter, which is one of the disadvantages of using this approach. We're working with time series data. Of course, we don't expect independence of observation anymore. And this is actually showing that the correlation that we have. Now, how do we now, in a way, solve this problem? You're going to see what I'm going to do next. Now, I need you to take a look at what I have here. We want to do bootstrapping. So what do I expect the bootstrapping to do for me? Because of the fact that there's a high correlation here, there's going to be a wider range of the interval for each of these parameters. When I bootstrap, okay, when I bootstrap, you remember the other time, bootstrapping, where we sample with replacement, where it's not as if we're going back to the population, but we want to provide a general, several versions of the sample. Here we're choosing 200, and we find a confidence interval. Okay, for the parameters, this is what we actually have. Let's see. Initially, what was the range of L infinity? 33 to 399. Look at that range compared to the new range after bootstrapping. Okay, so we expect that the bootstrapping effort should lower the range, okay, for each of that. We can also look at the the distribution of each of the parameter. Don't forget, we bootstrap, right? We bootstrap 200 times. Bootstrap it 200 times means I'm actually going to have 200 values for L infinity, 200 values for K, 200 values for T0, okay? And I will need to get a distribution for that. You can see the distribution now in terms of the histogram. Some are skewed. Some is kind of approximately normal. Now, what I observe is, I said, for example, one is 95% that the Brody growth coefficient K is between the 0.16 and the 0.53. And I said the histogram of the bootstrap is also show the distribution of K. It's approximately normally distributed. I'm talking about this guy, the K1. Of course, we know the other ones are kind of skewed. Okay. And I said, whereas the distribution of L infinity and T0 are much not normally distributed. As you can see, they are not. So the difference between the asymptotic and the bootstrap confidence interval are much greater. For L infinity, and T0 than for K. I think there's more or less an agreement for K, but don't forget what you have here, the interval there was based on the assumption that the sampling distribution of L infinity, K, and T0 is normal. You know that, right? That was the assumption. Okay. And you can see, that is kind of violated. Now, another thing that we can choose to do is to test hypothesis about K. Why are we interested in K? K is highly significant, when you talk about modeling the length of fish. I told you the other time, they said the body growth, that very K, becomes smaller when the shark is actually growing older. And that is why we may want to test hypothesis about that particular K. Under the null hypothesis, K equal to 0.5. In biology, I know in fishery ecology, they're going to have a particular value. Maybe they got a threshold for K, and maybe the threshold is 0.5. And they basically want to test whether it's going to be less than that. So I'm actually using, I'm actually going to use H-test, and I'm using a Bootstrap 1. And the p-value that I got for the test, 0.0735, 0.07538. The p-value is greater than 0.05 level of significance, and because of that, you're going to fail to reject the null hypothesis. Then you're going to see that my hypothesis here was based on the bootstrapping. Now, when you take a look at what I want to do here, I want to use my model to make a prediction for length for a fish that is age 8. Okay, so the essence of looking for a function that depicts the relationship between the length of the fish and the age, the essence is to make a prediction if I know the values of age. Okay, so when we use the model, the fit typical, that will give me 349.2. Okay, now when I use the one for the bootstrap, if you take a look at the one I actually have in here, the one you're actually going to see the confidence interval is from 340.6 to 358. So because of that, I'm actually going to say the mean length. Don't forget what we're predicting is an average length. Not the actual length. Don't forget, when I started, I show you a nonlinear mean function. Okay, our prediction is average. Okay, so thus, the mean length of all age 18 male, don't forget, we focus on male, Atlantic croaker is between 341 and 358. But let me tell you this. How do I know our model is going to perform great? Then our model must follow assumptions. Assumptions have to be met. Okay, we have assumptions in linear regression. We also have in non-linear, even though some of them may be relaxed, but we still have assumption. Also, I said a non-linear regression, okay, as it has been described here, require that variability about the model is constant. We require assumptions of homoscedasticity, which we call constant variance. Not only that, we also expect the error to be normally distributed. Okay, so and not only that, there shouldn't be any inflection point, an outlier. If this assumption hold, then we can trust our model. So how do we investigate that? How do we investigate normality? How do we investigate constant variance? If we want to investigate normality, we can go graphical using a residual plot. That's why you said recede. We did the same in a linear model. So we need a recede plot for typical. The fit typical is what we fit in, and the histogram. Okay, and in the residual plots, will tell you whether there's a constant variance. Don't forget, in linear regression, we use residual plots to investigate linearity and constant variance. But this is a non-linear regression. We don't even investigate linear. We're not interested in that. The focus is going to be on the constant variance. That's why we need residual plots. And of course, the normality histogram. Okay, so take a look at this guy now. Okay, you can see it too, right? Okay, so what I'm trying to show you now is a residual plot and the histogram of residual. Okay, the essence of the residual plot here is we want to investigate whether the assumptions of constant variance hold. Okay, but from what I'm seeing here, there's a violation. And if you take a look at the histogram, there's a deviation too from normality. That's kind of skew, right? You take a look at that. Okay, now how can we now fix the problem? You know what we've done in linear regression. When there's a problem, we transform. We can introduce log, we do those, square roots. We got different kind of transformation. But in the case of Bertalanffy growth model, we're going to consider the way error enters the model. We want to see, the multiplicative log normal error structure. We are talking, if you take a look at equation 12 and 13, they are not the same. In one, error enters the model multiplicatively. In another one, error enters the model additively. Which model am I talking about? Bertalanffy growth model. The way errors, if you take a look at 12 and 13. Okay, now when you take a look at 12, okay, when you take the log of equation 12, that will give you 13, right? Do you see that? But in equation 12, the error there is multiplying, the exponential raised to power error is multiplying the Bertalanffy model, right? Can you see that? Now, when you have a multiplicative, it will be easy to introduce a log, and the log is just going to give you an additive form. Now, and that was why I said a multiplicative error structure essentially assumes that the variability changes, usually increases in proportion to the expected value of the response variable, which means when you are using the multiplicative error structure, that we actually solve the problem of a violation of a constant variance. You remember in a linear regression, when there's a violation of a constant variance, what do we normally use? We go for weighted least square. Because in the weighted least square, the weighted least square already assumed, okay, a non-constant variance. In statistical analysis, we want a situation where the nature of our model will commiserate with reality. Now, I want to fit this model now. It's fitting the model now because I'm having a log. Log of what? Log of the Li. Take a look at that. This is more or less like I'm transforming the Bertalanffy growth model with using the multiplicative error structure that I also call the log normal error. Okay, so which means I'm actually going to log, right? I'm going to log the variable. Well, what am I logging? Okay, you can see what I'm actually logging now. The T1, the response variable. When I do that, I'm going to do what I did before. And I finally, I'm going to do what I did before, where I'm actually going to get initial values. Then I'm actually going to run that. But what I'm running now, don't forget, I got a log now. Okay. Now let's look at the results. We got a result right now. Okay. Now looking at this result, let's go into the confidence interval. We got this at the confidence interval. And this is a correlation matrix. Let me tell you this. The essence of transforming the Bertalanffy is not to address violation of independence. Don't forget, we're working with the time series data. But the reason why we are taking a log, why we are introducing multiplicative error structure that I also call log normal error structure is to address other violations. Now, how do I know whether that work? Which violations am I talking about? What I'm trying to show you now is when I'm comparing the additive error structure and the multiplicative error structure. The additive error structure was the one we feeded before. The multiplicative one, the one we just feeded. But what was the essence of introducing multiplicative error structure? Is basically to see whether we can address the violations of normality and the constant variance. What am I going to do again? If I want to know whether the intervention has worked, then what I'm going to do is to investigate my residual plot and the histogram. I actually want to investigate whether the assumptions of constant variance is still going to be violated, and whether the assumptions of normality. Oh my God, take a look at what I have now. Take a look at what I have now. This is kind of an improvement. And that was why I said the residual plot and the histogram from fitting the typical the Bertalanffy group model with the multiplicative error, to that. So I can say it's just slightly less, the slightly less skewed, as compared to the other time when it was heavily skewed, which is an improvement. Okay, if that is an improvement, I think I'm going to reserve this area for next time, because what we want to do next, this is very, very crucial. This is when we have different kinds of, do you know that within Bertalanffy growth models, we can compare a lot of models. For instance, if I basically talking about, if I have two different groups where I'm talking about male and female, you know what I've been using so far? I've been concentrating on male, right? Now, on male fish, right? What I'm going to start next time from slide 26 is when I have two groups of fish, male and female, okay, and I fit Bertalanffy for male, Bertalanffy for female. Now the series of models I'm actually going to have is to consider whether they have the same values of K, or the same value of L infinity, or the same value of, that's what I'm going to be comparing. And that's what I'm going to be calling comparison of the two groups, whether they have some stuff in common and so on like that. And of course, I provided all this. And in whatever I do, I also need to put into consideration, whether assumption hold. Like I said, I'm going to start from slide 26 on Friday. Any question before I go today? What is the takeaway? There's going to be a violation of independent assumption because it's time series data. But we don't want a situation where there is going to be violation of normality and constant variance. And that is the reason why the way error enters the module matter. When error enters additively, there could be violation or not. But the only way we can solve the problem when error enters additively is when you allow error to enter multiplicatively. When error enters multiplicatively, that was what led to idea of taking the logarithm of the response. And we got a way to investigate whether the intervention has worked. The way to investigate is to use a residual plot to investigate whether the assumptions of constant variance hold, and to use the histogram to see whether the assumption of normality hold. Okay, this is where I'm going to stop today. Like I said, latest 11:59 p.m. tonight, you're actually going to see a grade for midterm 2. So make sure you stay safe and have a lovely day. Bye for now, everyone.